Wichita, Princeton University, and he's now in his studies in Princeton, has been for quite a while. As you probably know, the theme of his work has been, perhaps we'll summarize as dynamics, but despite the problem of not only galaxy dynamics, where his recent focus has been black holes, but if you've read Astro PH, he can also explain to you why human-made satellites don't fall down, and he will give another scale talk about dynamics here. And Scott is also an honest man. Many people give 2 talks, but hide it in the title. I presume that is what it means.
Thank you. So, as Hans Welter indicated, I'm going to give 2 talks loosely related by trying to understand aspects of the distribution of orbits in planetary systems. We can only do this, of course, because we now have more than one planetary system whose orbits we have some information on. So to start, I'm just going to give an extremely quick review of how we know what we know about the orbits of extrasolar planets. Most of this should be familiar, so I'll go quickly. The most successful early method of determining finding exoplanets was radial velocity variations on the host star, which arise as the planet and the host star orbit around their common center of mass. The current accuracy of these measurements, periodic Doppler shifts in the spectra, is about 1 meter per second. For comparison, Jupiter, if we're looking at the solar system from 10 parsecs away, Jupiter would induce a velocity of the sun of a little over 10 meters a second, so it would be easy to detect. Earth would induce 10 centimeters per second, and so is beyond the level of current technology. So we could see Jupiter, but not much else. The second method is transits. I should apologize, by the way, these nice animations I got off the web and I forget where I got them. So if anybody here is responsible for them, please tell me and I'll give you credit in the future. So in the cases where the planet happens to be oriented, so it transits the host star, you get a rich set of information. You get the primary transit as the planet goes in front of the star, the secondary transit as the planet goes behind, and a sinusoidal variation due to the phases of the planet as it's illuminated by the star. The detection of planets by transits really took off with the launch of the Kepler spacecraft. Basically, it has a large camera which stares 24 hours a day, 7 days a week for 3 years at one field of the sky with about 10 to the 5th stars. It was able to achieve photometric precision of 30 parts per million, far higher than you could get from the ground. And for comparison, that means that both Jupiter and the Earth would be easy for Kepler to see if it was oriented so that it saw them transiting the sun. Kepler's reaction was failed in 2013, but there's a redesigned K2 configuration which continues to look for planets but on shorter timescales. An illustration of what Kepler can do comes from looking at one star that was detected from the ground that happens to be in the Kepler field of view. This is a folded light curve from 2 months of data from the ground. For comparison, this is a 1% photometric variation, which is about what Jupiter would provide around the sun. The analogous Kepler light curve looks like this on the same scale. If you multiply it by a factor of 7 and then a factor of 100, you can see the secondary transit marginally here and very clearly here, as well as the sinusoidal variation due to phases. So all of the features that you would expect to see are visible in the Kepler light curve. So it provides a rich set of information. There's something like 3,400 planetary candidates found from Kepler. Most of them are just candidates because they haven't been verified by radial velocity measurements and there's a false positive rate of maybe 10 or 20%, but it's nevertheless a remarkable harvest of objects, most of which are certainly real. This is a summary of the data. Of course, Kepler measures transiting planets here. Kepler measures radii. We had to convert them to masses using mass-radius relation. The transits only measure mass times the sign of the inclination, so I've just assumed they're edge on, which is not too far from the truth. So the radial velocity measurements in red give you the m sine I, the orbital period, semi-major axis, and eccentricity. The transit observations give you the planet radius, the orbital period, and semi-major axis. You can see on this that Jupiter is easily detectable from the radial velocity surveys. The only problem is that its orbital period is long enough that the radial velocity surveys haven't really gone for a long enough time to make it easy to detect things well outside Jupiter. Venus would be possible for Kepler to detect. Earth is a little bit outside its the detectability of planets from Kepler, simply because its orbital period is a year. Kepler was only up through 3 or 4 years, and you have to see 3 transits to be confident that we found something. There are at least 2 populations of planets that that are, if not surprising, at least novel from these surveys. One is a set called the hot Jupiters, objects with a mass comparable to Jupiter, but found in very small orbital periods. At orbital periods, a factor of 100 to 1,000 smaller than Jupiter's, and therefore very close to the host star. The other is super Earths, that is, planets with a mass larger than Earth's, but smaller than Uranus and Neptune, somewhere in between the ice giants and the terrestrial planets, population of planets that we simply don't have in the solar system. Okay, so that's the 5-minute summary of what we're learning about exoplanets. Let me go to the first topic. Are planetary systems really flat? This is largely based on research I've done with a series of collaborators who have been either graduate students at Princeton University or postdocs at the Institute. So this question may seem like an unusual question because obviously the solar system is flat. The maximum inclination is 7 degrees, although this is only after we got rid of Pluto. Moreover, the inner satellite systems of Jupiter, Saturn, and Uranus are flat, and so it's reasonable to suppose that all planetary systems are flat, but nevertheless, this is a question that we should try to answer empirically. You can't really answer it from the radial velocity measurements. As I said, the radial velocity surveys only give you m sine I. They don't tell you anything about the inclination. And so the only information that you get from radial velocity surveys about mutual inclinations is in the rare cases where you can measure the mutual planetary perturbations and get some information on the inclination from detailed modeling of the dynamics. The only case in which that can be done cleanly is a set of planets that were discovered by Alex Volchan in the 90s around a pulsar. There the inclinations are rather small, but the pulsar planet system almost certainly formed by a completely different mechanism from planets around normal stars, so it's of limited use to us. You can do better by looking at the Kepler planets. So there are a variety of methods of trying to constrain the inclination distribution from the Kepler planets. The first is to notice that selection effects really disfavor the discovery of multiple planets in transits if the mutual inclinations are high. The mutual inclination is 0, of course, then if one planet transits, the other one has to transit, the other one doesn't have to transit, but it's much easier to have both transit if they're in nearly the same plane than if they have a big inclination to one another. As I said, that selection effect isn't present in radial velocity surveys, and so if you compare the numbers of 1, 2, 3 planet systems in the radial velocity surveys and the transit surveys, in principle you can constrain the inclination distribution. So if you look at the Kepler survey, It looked at this number of stars, and at least in, I think it's 18-month or 2-year data release, at this number, 1 planet, 2 planet, 3 planet systems, and so forth. If you look at all the combined radial velocity surveys, the analogous figure to the total number of stars is really completely unknown because many people have done the surveys. They don't always tell you all the stars they've looked at. They don't report negative results and so forth. So this is a number that you simply don't know. But the number of 1, 2, and 3 planet systems and so forth is known. So the first thing you can do as a really crude analysis is just look at the ratio of 1 planet to 2 planet systems. So just divide this number by this one, you get almost 7 in both cases. Since I've said that high inclinations discriminate, make it harder to find multiple planet systems in a transit survey, this already the fact that these numbers are almost equal already tells you that the inclinations are small. In fact, since they're almost equal, it tells you that typically the mutual inclination must be less than the size of the planet orbit compared to the radius of the star.
Scott, is the solar system flat in that sense? That
In what
from
sense?
one given direction, most of the planets would transit?
No, but it is flat in the sense that the inclinations that you derive are comparable to what you get from Kepler systems. Okay, anyway, so I looked at this in some detail with Subo Dong. We didn't believe this simple argument, so we spent many months of work trying to make a more detailed model, but the answer is basically the same. There's a strong constraint that the mutual inclinations are small, with upper limit on the mean inclination of 5 degrees. There's a second, completely independent way of doing this. If 2 planets have circular and coplanar orbits around the same star, the duration of the transit tells you the impact parameter of the star. The ratio of the impact parameters if the inclinations are 0 should be the ratio of the semi-major axes. The ratio of the semi-major axes you can tell from the ratio of the periods in Kepler's law. And so the combination of the transit duration and the ratio of the periods gives you an implicit constraint on the mutual inclinations. This was worked out again in detail in a paper led by my former student Dan Fabricate, and they found the RMS inclination between 1 degree and 2.5 degrees for the Kepler planets. The great advantage of this method of doing it is that it's entirely based on Kepler data. It doesn't require this kind of messy comparison, the radial velocity of the Kepler samples. The disadvantage is that this looks like an extremely strong result because it's a long way from a radian, but it's not because the method loses its power, again, if the RMS inclinations are such that the impact parameters are separated by more than the radius of the star. So it only would give you a signal if the mutual inclinations were less than about 3 degrees. This looks like a strong signal, but it's not strong by many standard deviations. There's a third way to look at this problem. In some cases, you have a multi-planet system where only 1 planet transits, but you can detect a second planet because by transit timing variations, the gravitational perturbation from the planet causes the transits to be either periodically early or late. Because the second planet isn't transiting, the selection effects favoring low inclination systems are relatively weak. And so the inclinations that you measure from modeling the transit times should be a reasonably fair sample of the actual inclinations. There are 2 cases where this has been done. In one case, they derived an inclination less than 4.5 degrees. In the other case, they derived 9 degrees with relatively large error bars. So again, both of these are consistent with low inclinations. By now, there's 7 or 8 papers. I've talked about this one, and these 2, but they're all consistent in the sense that they all give relatively low inclinations. And the implication is that the average multi-planet Kepler system is about as flat as the solar system, which has an RMS inclination 3 degrees. And if you think about it, this is the first, and I think really the only evidence that extrasolar planetary systems are formed from a disk, as Laplace originally proposed. That is, there's a huge body of very good work on the theory of forming planets from a disk, from a protoplanetary disk. But if you ask for direct evidence that planets were formed from a disk, the exoplanets were formed from a disk in the same way as the solar system. As far as I know, this is it. So this is very nice. From the Kepler planets, we've concluded that things are flat, they must be formed from a disk. This is just what happens with the solar system, so everything is fine. On the other hand, there are a few worrying problems. First is that in most disks we know of, whether it's the asteroid belt, the Kuiper belt, stars in the solar neighborhood, and so forth, the eccentricities are almost the same as the inclinations, maybe bigger by at most a factor of 2. So if the RMS inclination was 3 degrees, the RMS eccentricity ought to be between 0.05 and 0.1. That's what works in the solar system. However, for the radial velocity planets, we can measure the eccentricities. This is the distribution of eccentricity versus orbital period. The eccentricities are small, at very small orbital periods, because at the small orbital periods there's tidal damping. And on average, if you go outside this region, the RMS eccentricity is more than 0.3. So far larger than you get here. This is a worry. There are a variety of possible explanations. None of them are very satisfactory. This is for all planetary systems. If you look at multi-planet systems, the eccentricity is a little smaller, but still far too large. There's a weak trend of eccentricity that it decreases as the planet mass goes down. And the Kepler planets do have smaller masses on average than the radial velocity ones. That's not enough to fix things. Maybe the transit surveys and radial velocity surveys are somehow measuring quite different populations of planets with a discontinuous change in the eccentricities. Or maybe the eccentricities are much bigger than the inclinations. There are some models of planet formation in which that happens. And in this one particular case, there's a clean measurement from transit timing variations of both the eccentricity and the inclination. The eccentricity is 0.8 and the inclination is quite small. Which of these is correct at the moment, we have no idea.
Scott, are there any anthropic arguments for the solar system to be a low eccentricity system?
I'm not going to answer that. Okay. The second concern is that in many systems, the stellar spin axis and the planetary orbital axis are misaligned. This is determined by very elegant observations using the Rossiter-McLaughlin effect. And it's illustrated here. You have a star that's blue shifted here and red shifted here because it's rotating. As the planet transits in front of it, it first occults the blue shifted part and then the red shifted part, and that gives a characteristic wiggle in the radial velocity curve. If the planet is inclined, if the planet orbits inclined, the shape of this wiggle changes. In the limited case where it is retrograde, this wiggle would be flipped. By fitting the wiggle, you can measure the projected obliquity, that is the angle in the plane of the sky between the spin axis of the star and the orbital axis of the planet. This measurement has now been carried out for something like 40 or 50 systems. This is an example of one of the better sets of data, and this particular, so this is the transit light curve, this is the radial velocity curve. This fits the simple theoretical model extremely well and gives you a projected obliquity that's consistent with 0. However, if you look at all the systems where this has been measured, so this is projected obliquity versus the distance of the planet from the star divided up according to the effective temperature of the star. And roughly speaking, you can describe this as a population of planets that have near 0 obliquity. That is where the spin axis and the orbital axis are aligned. And then another population containing almost half of the planets in which the obliquities are distributed more or less isotopically. The conclusion from this is that some dramatic event has randomized the orientation of the stellar spin relative to the planetary orbit in about half of these systems. There are two ways to do this, of course. Either you leave the planetary orbit the same and change the spin of the star, or the system of planetary orbits is not flat. On average, it may be aligned with the equator of the star that the individual planet orbits aren't. The first of these, there are a variety of ways of doing this. The simplest way is to have a giant planet collide with the star, because then it brings in enough angular momentum to flip the stellar spin. But because of limitations of time, I'm going to focus on the second of these two possibilities. These are all planets that are quite close to the host star, and so in order to understand whether it could be that the planetary system is not flat, we have to talk a little about how these planets form. So all of the objects that we see here are in fact in the category of hot Jupiters. That is, they're all in this region in the plane. The reason for that is they have to be big so you get enough signal to noise to measure the Rossiter-McLaughlin effect, and they have to be close so that they're likely to transit. The difficulty with this is that it's very hard to form gas giant planets like Jupiter so close to the host star. There's not enough metals in the disk to form the core of the hot Jupiter, and the disk is so hot that it's very hard to collapse the material to form the star. This has led to the general belief that these planets form in larger radii. It's plausible that they formed in this cluster of giant planets out here at periods of several years, like Jupiter, and then some mechanism made them migrate in to much smaller radii. There are two possible mechanisms for migration, generically called disk migration and high-eccentricity migration, and I'm going to briefly describe both of them. So in the case of disk migration, it arises because the giant planets form while the protoplanetary disk is still there, and then gravitational torques between the planet and the disk transferring the momentum between the planet and the disk. If you imagine the names of type 1 and type 2, there's now even a type 3 and I think a type 4. These are the most important. Type 1 occurs for low-mass planets. They launch spiral waves in the disk, and the mass in the spiral waves exert torques on the planet. One spiral wave pushes the planet out, the other one pushes it in, the one that pushes it in generally wins, and the planet spirals in on a remarkably short time scale, typically 10 to the 4th to 10 to the 5th years, much shorter than the time it takes for the disk to dissipate. The planet has a much higher mass, it will actually open a gap in the disk, and then the planet spirals in with the disk material due to viscous stresses within the disk. This has a somewhat longer migration time scale, but still generally short compared to the lifetime of the gas disk. This is a very robust mechanism. It almost always occurs in numerical simulations and analytic calculations, but it does have some problems. The first is that it's so robust that typically all the planets migrate into the star. And in fact, numerical models which attempt to synthesize the population of planets have a dial in which they ad hoc or reduce the migration torques by a factor of somewhere between 10 and 1,000 in order to reproduce the observations. So that's not so good. You can fix that by saying migration stops at the inner edge of the disk, leaving the planets close to the star. But the trouble with that is that there's no pileup of planets at small semi-major axes. This is the same diagram I showed you before, and you can see that inside this clump at a few years orbital period, the distribution of giant planets is relatively flat in semi-major axis or orbital period. There's no sign of a pileup at the inner edge of the protoplanetary disk. that you might expect from disk migration. A related problem is that you can name the population planets out here the warm Jupiters, in contrast to the hot Jupiters in here. A related way to ask the question is, how did these form if they got here by migration? Why did they stop partway through? Since the migration timescale is short compared to the lifetime of the disk, if they start to migrate, they should keep migrating. So why do you have a population of planets well outside what must have been the inner edge of the disk? So that's the third problem. Where did the warm Jupiters come from? We don't know where the eccentricities came from. Again, the giant planets had an RMS eccentricity bigger than 0.3, but interactions with the gas disk certainly ought to damp the orbital eccentricities. It's very hard to understand why they're not on merely circular orbits. Of course, we also don't understand how the obliquities were excited, because migration in the disk should leave you with a flat system of planets, not ones with a big relative angle between the spin of the star and the orbit of the planet. Yet another problem is, why aren't there more planets in resonance? If you have more than one planet that's migrating through the disk, if the planets approach one another, they'll inevitably get trapped in mean motion resonances, where the orbital periods of the two planets are in the ratio of 2 to 1 or 3 to 2, something like that. That was well understood before the Kepler data came back. Kepler gave us enough planets that you could plot the distribution of period ratios, and this is the distribution. So what you would expect is a huge pileup of planets near the 2 to 1 resonance. In fact, there seems, if anything, to be a gap. A huge pileup at the 3 to 2 resonance, where there's a little bit of a pileup, but certainly not as much as you would expect, and no sign of any enhancements in any of the other resonances. So we don't understand why there aren't more planets in resonance. Again, there are ways out of all of these problems. I'm just trying to make the point that the naive predictions from disk migration simply don't work very well. So I would say the scorecard for disk migration is a fail. The second mechanism is high-eccentricity migration. It's quite different. It postulates that some process has excited the eccentricities of some planets to very high values. This eccentricity, the pericenter of the orbit, is sufficiently small that it comes within a few times the radius of the star. And when that happens, either the planet will collide with the star eventually, or it'll be tidally disrupted, or because of tidal friction, it'll gradually lose energy and settle into a circular orbit close to the star, and thereby produce a hot Jupiter. One natural explanation of this is that natural prediction is that it says the obliquities should be high, because this process isn't going to keep the planet in the orbital plane, in the equator plane of the star. It also says that this process should kick out any other bodies close to the star, so it should say that hot Jupiters have no nearby planetary companions. And in this one case, Stefan et al. Found 0 cases out of 63. So it has 2 successful predictions. What it doesn't explain is what process excites the eccentricities in the first place. And the most likely process is Lidov-Kozai oscillations. I'll give a brief, although many of you may be familiar with these, I'll give a brief description of them because they're pretty interesting. They were discovered by Lidov in the early 60s and popularized by Kozai. They were ignored for a long time. This is a plot of the citations for Lidov and Kozai, which you can see were basically 0 until about 15 years ago, and since then have been rising exponentially, no sign of leveling off. The reason for that is not just the interest in exoplanets, but they've turned out to be applicable to an extraordinary variety of astrophysical systems. Lidov was originally thinking about artificial satellites, Kozai about asteroids, but they're relevant for binary stars, blue straggler stars. They may even be a channel for making, the dominant channel for making type 1a supernovae. They're relevant for supermassive black hole mergers, Kuiper belt binaries, and so forth, and so on. The basic mechanism is quite simple. It arises most simply in the case where you have a test particle orbiting a star here and some third body out at much larger distances. In the Kepler orbit is a closed ellipse, so the ellipse has a fixed orientation. When you add a third body, it creates a torque on the ellipse. But the point is, because the orbit orientation is fixed, the torque is also the only thing that changes the orientation of the ellipse. So the lever arm of the ellipse is basically fixed, except for this torque. So no matter how small the extra force is, it'll change the angular momentum on a time scale of order 1 over epsilon, but the orbit will only precess on that same time scale. So it has an effect which is can have an effect which is of order unity, no matter how small the perturbation may be. If you apply this to the simplest case of a distant companion, what you find out is that if the test particle is on an initially circular orbit, that orbit is stable if and only if the mutual inclination between the planet and the distant companion is less than about 40 degrees. Above that inclination, circular orbits don't remain circular, and they start undergoing large-scale inclination and eccentricity oscillations. The simplest example of this is due to Lidov. He said, suppose you take the lunar orbit, which is now roughly in the ecliptic, and just turn it so that it's 90 degrees from the ecliptic, leaving all the other orbital elements the same. If you do that and follow its evolution, it'll crash into the Earth in about 5 years. That's a particularly short period oscillation because the sun is relatively strong. It has a strong tidal force. As you change the mass and separation of the companion, if you affect the period of the oscillations, but not the amplitude. So this is a very attractive potential way of getting high eccentricities whenever there's some sort of third body in the system. The simplest example of a third body would be a binary star. Binary stars are likely to be misoriented, their orbits are likely to be misaligned with the plane of the planetary orbit because the stellar spin is misaligned with the orbit of a binary, and all binaries with semi-major axes larger than about 50 AU. So this is a possible way of generating the high eccentricities that will excite the Lidov-Kozai oscillations. When this was first recognized, some people made the bold hypothesis that all of the eccentricities of all the planets are excited in this way. That's actually not correct for several reasons. First, if you just look at the plot of orbital eccentricity against orbital period and mark the stars that are binaries, you don't see any clear correlation between high eccentricity and the presence of a binary. However, if you look at the very highest eccentricities, these exceptional planets with eccentricities of 0.9 or larger, you see that almost all of them are binary companions. So it's possible that this simple mechanism is the source of some of the very high eccentricities that you, unusual orbits that you see in extrasolar planets. Other problems, you can suppress the Lidov-Kozai oscillations if there's some other source of precession. One is another planet, a more exotic one is general relativity. There are a number of cases where general relativity, planets in known binary star systems where it's clear that the general relativity is suppressing the oscillation. So one of the unexpected conclusions is that you can't understand planet formation without including general relativity. And the final concern is that if you actually go through detailed simulations, which have been done most cleanly, I think, by my student, Cristobal Petrovich, you simply can't reproduce the correct numbers of hot Jupiters, the correct semi-major axis distribution, the correct obliquity distribution, or the presence of warm Jupiters. So this mechanism must work at some level, but it's not explaining all of the hot Jupiters. A more promising mechanism is a coplanar outer planet on an eccentric orbit. This will introduce oscillations similar oscillations to Lidov-Kozai oscillations. And again, Cristobal has gone through the exercise of simulating this. He produces, with plausible initial conditions, hot Jupiters in about the right percentage of systems. The semi-major axis distribution is about right. He only produces systems with relatively low obliquity. Remember I said that the Rossiter-McLaughlin observations suggested there were two populations, one with low obliquity and the other with isotropic obliquities. So this only produces low obliquities, so it's possible at least that this mechanism produces the half of the hot Jupiters that have the low obliquities. But I'd say that high eccentricity migration is not working perfectly, but it's working better than disk migration. Okay, let me just summarize what I've said so far before going on to the second part of the talk. We now know that the multi-planet Kepler systems are about as flat as the solar system. That's strong evidence that they form from a disk, but this evidence is difficult to reconcile with the relatively large eccentricities and obliquities that we see in giant planets discovered by radial velocity surveys. The discrepancy might be because the Kepler planets formed by a different process. Maybe the giant planets migrated and the Kepler planets formed in situ. It might be that the eccentricities are much larger than the inclinations because we're measuring inclinations for Kepler planets and eccentricities for radial velocity planets. There are very few systems where we can measure both. It's possible that some processes tilted the stellar spin relative to the planetary orbits, like torques in the Earth cluster, or maybe a collision with the giant planet. I would say these are clues, but no more than clues to understanding what I think is one of the basic unresolved questions of exoplanet formation. How do giant planets migrate to the small radii? There are two competing theories, disk migration. I think it's safe to say that no prediction made by disk migration was proved to be correct. One of the nice things about exoplanets is that the pace of discovery has been so rapid that theorists can make a prediction which is proved or disproved within a year or two. Disk migration predicts all the planets going to the star, they all pile up at the middle, the obliquities are low, they're all in resonances. All of these were definite predictions and they were all completely wrong. High eccentricity migration has the virtue relative to disk migration that you can calculate what's happening with a reasonable degree of certainty. I'd say it's had partial success in explaining many of the properties of the hot and warm Jupiters, but not complete success. So the story here, I think, is still unfinished. Okay, so let me go on to the second talk. Whether statistical mechanics is useful for describing planetary orbits. So if you've been asleep, you can wake up and start fresh. This is an old subject. There are many, many bad examples of trying to explain the spacing and other properties of planetary orbits from first principles. This goes back to Kepler and putting the planets in the five perfect solids. Nevertheless, I think it's reasonable to keep trying. The reasons are the first time we now have a large statistical sample of planet candidates with well-defined selection effects and multi-planet systems, so we have data to compare with. N-body simulations can follow the evolution of planetary systems over time scales shorter than, but not that much shorter than the likely lifetime of the system, so we can do numerical experiments. These numerical experiments were first done on the solar system, and they yielded a number of interesting features which suggest a rich dynamical behavior that might be described by statistical mechanics. The orbits of all the planets in the solar system are chaotic. They have very short Lyapunov or E-folding times, only 10 to the 7th years. So the solar system really is sensitive to initial conditions. When I came here from the US, the change in the tidal field on Jupiter due to my movement is sufficient to change Jupiter's orbital phase by a factor of pi over the next 5 billion years. The outer solar system is full in the sense that there are no stable orbits between Jupiter and Neptune. If you try to put a test particle anywhere between Jupiter and Neptune, it can't survive, which suggests that there used to be more planets there and that they got ejected or collided with one of the other planets. And in fact, some of the planetary orbits do evolve chaotically. The most extreme example is Mercury, in which case for Mercury there's a 1% chance it would be lost from the solar system by colliding with the Sun or Venus or even Earth before the Sun turns into a red giant. So these are all suggestions that the solar system has a rich and chaotic dynamical history, and maybe there's some room for constraining it through the statistical mechanics of orbital chaos. This is just a picture of what I said about Mercury. This is calculation of the evolution of Mercury's orbit, including all the other planets in the solar system. The lowest order relativistic effects were 5 gigayears. This is something like 2,500 repetitions of the calculation, in which Mercury's initial condition was changed, I think, by a Gaussian with a standard deviation of a millimeter. Because it's chaotic, that's sufficient to explore the chaotic region, and you can see that in some fraction of the cases, Mercury reaches an eccentricity very close to unity, which is sufficient to cause it to have some catastrophic encounter with the Earth or Venus or someone else. So this general idea that statistical mechanics might be useful can be tied into standard theories of terrestrial planet formation. Those theories suggest that the early stages of formation yield a few dozen bodies, roughly Mars size, which are sometimes called planetary embryos. Those embryos are on well-separated, low eccentricity orbits because they're small bodies, small planetesimals, and friction from those planetesimals keeps them on nearly circular orbits. But eventually the small bodies are incorporated in the embryos and disappear, and at that point the gravitational perturbations from the embryos gradually excite the eccentricities. The orbits cross, they collide, the number of embryos shrinks until eventually you're left with a much smaller number of planets in well-separated, stable orbits. This has various names, of which the one I'll use is giant impact phase. And so, again, the hypothesis is that maybe this phase tends to produce a set of planetary systems with statistically similar processes, eccentricities, inclinations, mass distributions, and so forth. Okay, let me try to quantify this. The range of strong interactions between planets on circular orbits is defined by the Hill radius, which is basically the semi-major axis times the cube root of the ratio of the mass of the planet by the mass of the sun. If you look at multi-planet systems where you set down a bunch of planets of similar masses and similar separations, what you find is that those systems are stable if the closest approach between each pair of planets exceeds some dimensionless number of order unity times the Hill radius. So in terms of semi-major axis and eccentricity, this is the pericenter of the outer planet, the apicenter of the inner planet, and as long as that's separated by more than some number of Hill radii, the orbits are stable. In this case, because both planets have masses, you use a slightly different definition of the Hill radius involving the sum of the masses. And for this dimensionless number, there have been a whole set of simulations. They agree reasonably well, and for, say, 10 to the 10th orbital periods, about the age of the current Kepler systems, the number is somewhere around 10 or 11, so I picked 11 here. Okay, so the way to apply statistical mechanics to this requires the ansatz, and the ansatz I'm going to make is that planetary systems fill uniformly the whole region of phase space that's allowed by stability criteria. This is sort of like the ergodic hypothesis, but it's not really because the ergodic hypothesis is for a closed or a compact phase space, and in this case the phase space is open. Nevertheless, the ergodic hypothesis has worked so well that it's worth seeing what it predicts in this case. The other approximation I'm going to make is to work not in an actual, the correct geometry, but in a model called the sheared sheet, which just replaces the Keplerian box by a rectangular box having shear. This is not a critical approximation, it just is a way of eliminating spatial gradients that complicate things unnecessarily. So with this ansatz, the n-planet distribution function is just the phase space volume, associated with each of the planets, which is here. A step function that says that the separation between the pericenter of the outer orbit and the apicenter of the inner orbit has to be more than k times the mutual Hill radius, where k is roughly 10. Well, that distribution describes everything about the planetary orbits. So that's all you need to know. The classical system that it's most similar to is something called the hard rod gas, or the Tonks gas. It's a standard analytically soluble model in statistical mechanics dating from the 1930s, which just says you have a one-dimensional box with a set of rods in it that can bounce off one another but can't interpenetrate. And that gives an almost identical distribution function. The only difference is this is a little more complicated because the eccentricity is involved in phase space as well as the position. And in both systems, you can work out the partition function, and the partition function, it turns out, depends only on something I've called the filling factor, which is the fraction of the radial interval that's allowed for the planets to fill up. Okay, so this is a repetition of the n-particle distribution function. To make it a little more accessible, I'm going to assume that the number of planets is large compared to unity, and that each I've lined up all the planetary systems, and I've assumed each one is a subsystem cut out from that system. This is, if you recall from your statistical mechanics classes, this is sort of equivalent to what people do when they make up a grand canonical ensemble. And when you do that, you get somewhat simpler expressions. So for example, the expression for the eccentricity distribution just looks like this. It depends on one free parameter, which is determined by the filling factor. But other than that, it's a simple expression that should be universal. Well, there's two steps in seeing if this works, right? The first is to compare it to simulations of the giant impact phase of planet formation, and the second is to compare it to the data. The first is cleaner because you know exactly what assumptions have gone into deriving the distribution. So this is a comparison for simulations by Hansen and Murray. That's the distribution of eccentricity. That's the fit with a single parameter, which is this parameter tau that went into the eccentricity distribution. So that's actually a pretty good fit. In fact, it's such a good fit that even before this, Hansen and Murray used that same expression as an empirical way to describe the results. So it's pretty clear that it must work okay. The second prediction is for the distribution of semi-major axis differences. Again, from integrating appropriately over this distribution function, you get a well-defined expression that depends only on this parameter tau. So this is again the same simulations. This is the fit. This has no free parameters because I used the value of tau that was determined from the eccentricities. So it also provides a very good description of the distribution of semi-major axis separations. You'd next like to compare it to the data. You can't compare the eccentricities because we don't have eccentricities for the Kepler planets. This is the distribution for the Kepler planets. You can immediately see that something's a little funny with this because according to the stability criterion, you shouldn't have anything less than 0 on the separation scale. In fact, there are a significant number of planets below 0 on this scale. The reason for that is almost certainly that you don't have a single unique mass-radius relation for the Kepler planets. There's scatter in it. That scatter was actually determined in a paper by Weiss and Marcy. So what I do is just convolve the theoretical distribution with the scatter that Weiss and Marcy estimated for the mass-radius relation. When you do that, you get a fit like this, which is, again, quite a good fit. There are two concerns. One is this tail, which might simply represent either systems that aren't formed in this way or cases where there's a planet that's below the Kepler detection threshold and therefore has been missed. The second issue is that the parameter tau is somewhat lower than it is here. The reason for that is almost certainly that in these calculations they assume that any planets that collided merged, whereas in a real system, planets that collide at high velocity will disrupt rather than merge. And if you make simple estimates of that, you get a value for the parameter tau that is lower than about that amount. This predicts the mean eccentricity for the Kepler planets of about 0.06. There's a variety of estimates, approximate estimates of the mean eccentricity. One of them is definitely lower than we predict. A more recent one is almost exactly the same as we predict. So on that, the evidence is still out. The last and perhaps most speculative possibility is the correlation between the mean eccentricity and the number of planets in the system. This has been pointed out by Lidov and Turner, that there's among the exoplanet systems, the more planets that are detected, the lower the eccentricity is. The solar system even fits on the same plot, although I think that's a real stretch to try to include it on the same plot. The mean eccentricity can be fit by, apart from the ones here where there might be missing planets, according to Lidov and Taylor, the fit is roughly n to the -1. The simple ergodic model predicts mean eccentricity goes like 1 to the n. This n is the same as that n, so I think the agreement here is actually pretty close. So is this the correct model for describing the orbital distribution of terrestrial planets? Well, almost certainly not in detail. But I think the advantage it has is that it's relatively simple. It provides predictions for all of the orbital quantities that you would like. It provides predictions for the correlations between quantities between nearby planets. And so it provides a kind of benchmark against which future observations can be compared. Is it correct? I want to close, instead of answering that, with a quote from a pair of famous statisticians. All models are wrong, but some are useful, and I think this model is certainly wrong, but probably useful. Okay, thank you. So, yes, it's correct that, I don't know if most stars form in clusters, but a significant fraction of them form in clusters. And there has been a lot of discussion of the possibility that interesting effects on the planetary system come about from interactions with the other cluster stars. most likely those effects are only important for planets at relatively larger radii, 10, 20, 30 AU, and so forth. In here, the Kepler planets and most of the radial velocity planets are at orbits of 1 AU or less. And I think for standard clusters, it's unlikely that the cluster environment will have any direct effect on those semi-major axes.
In the studies, those close to the can also be decided for the long-term.
Okay, maybe we should talk about that offline. Well, it is true, of course, that Lidov-Kozai can affect planets even at small radii. I think that for typical cluster densities, the effect of the Lidov-Kozai oscillations is relatively small, but I would argue that if I talk about binary stars, it's the effect of binary stars on the planets. The effect of the cluster is likely to be quantitatively similar.
Going back to your first talk, you have effectively propagated the model of eccentricity migration. And what does this model predict about the hot Jupiters that we know have very low eccentricities?
Well, the hot Jupiters that have very low eccentricities are close enough to the star that tidal damping from interactions with the star reduces the eccentricities to near zero. So roughly speaking, these systems evolved from very high eccentricity and large semi-major axis down to much smaller semi-major axis and near zero eccentricity. So I think in terms of the eccentricities, this works fine for predicting the low eccentricities of hot Jupiters that are very close to the host star. For the warm Jupiters, which are further out and have higher eccentricities, that's more of a problem. I have simulations that I've done with crystal ball that shows that we can do a reasonable job of predicting the eccentricity distribution of the warm Jupiters from high eccentricity migration, but not a perfect one.
Okay, but I mean, because we have both, right? We have hot Jupiters that are very close in with both reasonably high and reasonably low eccentricities. So that's, it will not predict all of this population.
No, because it's a slow process, and some of the hot Jupiters are still in the process of migrating in, and therefore haven't had their eccentricities completely down. So one of the advantages of this mechanism is that it does make a definite prediction for the eccentricity distribution of hot Jupiters that are in the process of migrating in. That is, again, reasonably consistent with the data.
Okay.
How does the eccentricity depend on the mass of the central star? Is there any correlation?
There's not the, well, so one of the nice things about this is that you can go to exoplanet.org and they have an interface and you can plot anything you want. I haven't plotted that in particular, but I think the evidence is not very good because the eccentricities are only well determined for the stars with radial velocities. Most of the stars that have been the subject of good radial velocity searches are stars similar to the Sun, both because they have a better set of spectral lines and slower rotation and were easier to measure, and because then if you find a planet, it makes for a better press release.
I have only a very small comment. All your Venuses in your diagrams have the wrong orbital period. If you plotted it at 40 to 50 days, about it's 224 days.
Okay, well, I better fix that.
had a question about so you argued that the disk migration doesn't work to explain the properties, but you also said that actually all the models have very efficient disk migration. So does it mean that the timing of the formation of the planets and the dissipation of the disk is different than what is assumed? And how do you switch it off basically?
Well, that's a good question. So basically the problem is that the disk migration typically occurs on a time scale that's much shorter than the time that is believed to take for the disk to dissipate. So if you're going to if high eccentricity migration is the answer, then first the high eccentricity migration has to work. Second, you have to find some way to switch off the disk migration. There are a variety of proposals for doing that, but I don't think there's any consensus on whether any of them works reliably in most cases.
So what is the line of thinking to switch it off? What's the kind of proposals that are there?
So one proposal is that, the problem is that the accurate calculations of disk migration require high-resolution 3D hybridynamic simulations. So, for example, with type 2 migration, where you open up a gap, the belief is if the standard model, the standard timescale estimate assumes that the gap is complete, and that as viscous stresses push material in the disk inward, they in turn push the planet inward. However, if you do some high-resolution calculations show that the material can leak past the planet through the gap. That is, it's not zero density in the gap, but the material can leak past the planet, and that reduces the torque on the planet and allows the disk to flow past it on the viscous time scale. Also, if you do these calculations, you typically find that there's a spike in the azimuthally average density close to the planet due to gas that's on horseshoe orbits. That can also have a big effect, which can, in some cases, reverse the overall torque on the planet. So there's a lot of calculations a lot of computations that I think are only just beginning to be followed reliably.
How sensitive are the difference of your statistical model to the conditions, or the usual feeling of the phase space?
So when you say initial condition, you mean filling of the phase space?
So the step up to the phase space, how does that affect the predictability of the statistical model?
Well, so when I say you fill the phase space uniformly, I wouldn't quite call that an initial condition. That is, it's a product of, in some ill-defined way, of the process of giant impacts and building up the planetary masses. I don't quite know how to answer that because there's no alternative model to the ergodic model. That is, it's not a question of having two models to compare. The attraction to the ergodic model is that it's so simple, it allows you both to do analytic calculations and to not worry about the details of how particles diffuse in phase space. Obviously, one of the things you'd like to do is to try more realistic models and see if you get similar calculations, but the price of making the models more realistic is that the answers aren't going to be analytic, and then at some point you may as well go back to doing n-body simulations.
All right. One last question.
So when you were talking about various scenarios for Kozai effects, you mentioned binaries and you mentioned other planets. So there's also a possibility that you have some exchange with disk, which is around there. Can you also consider this mechanism for pumping eccentricity inclinations?
In exchange with the protoplanetary gas disk or with some residual disk that's left over?
With the residual disk.
That's of course possible. The Kozai mechanism requires an outer body which is either eccentric or inclined relative to the inner body. I would normally think that the disk would be, you'd normally think that the disk would be axisymmetric. So that means it would have to be inclined. If there's a big inclination relative to the planetary orbit, it would certainly act just like a binary star and cause Kozai oscillations. It would, of course, have to have enough mass in the disk so it had much more angular momentum than the planet. So you need a relatively massive disk, and a standard, low mass debris disk probably would do it.
All right, let me perhaps now draw the discussion to close. Scott will actually be in town through the rest of the week, mostly up at KIA, but I think on Thursday it hits, and otherwise send him an email if you want to talk to him. And the other point that I want to make